fluid flow in chapter 4, heat transfer in chapter 5, pedestrian flow in other chapters that have not been written. It's the same thing. Corridors, 90-degree corridors versus corridors that are at an angle. In the most modern airports, you find concourses bifurcating at an angle. Pay attention to where you walk. Now, the airport is being built by smart people on a completely empty territory. In old cities, that's not possible anymore. The first streets and alleys were built small scale, and small scale meant that the alley and the street were perpendicular because the house was basically rectangular in shape. The armpit of the first intersection is a house. But on a virgin territory, anything goes, and that's why in the jungle you see these, when you go, especially if you are in a hot air balloon above the jungle, you see the paths of these animals. And they have these bifurcations with an angle. The animals are not stupid. They're not making 90-degree turns. Listen, you should talk among yourselves and ask yourselves, what would it take for you to become vociferous? Yeah. Because when you're so quiet, I'm losing my confidence. Stepping in the direction toward more applications, but not stepping blindly. If I explore the unknown, why not, meaning new configurations for fluid flow, why not go back to the first item of technique, which is to try the simplest first. And here's a very good idea about something even simpler than what you've seen. You saw that the pressure drop along a duct with, let's say, laminar flow, meaning fully developed laminar flow, is equal to a constant multiplied by the mass flow rate, and then the length of the duct divided by the diameter of the duct to power 4. And you also know, this is known as the Hess Murray rule. I didn't tell you this, did I? Hess Murray. Which is that D at the bifurcation, D2 divided by D1 equals 2 to minus 1/3, which is a number of order 1. This is a story very similar to the comparison between the so-called Moody chart. Coincidentally, Murray and Moody start with the letter M. And in place of Hess, who is Swiss and wrote in German, was Nikuradze and Prandtl, who wrote in German. So let's say Nikuradze here. And both Moody and Murray were Americans who published more than 10 years later what had appeared in the German literature. Anyway, this result of the, this is a very important constant in fluid mechanics, was published by Hess, and then Murray, more than 10 years later, generalized it, published it in English in the US, and most people think this is called the Murray's law. It's not a law, it's a an aspect ratio. And Hess, he did not complain. He was the opposite of a loser. He got the Nobel Prize for for it. And he was a medical doctor. A lot of this. Here's another thing you better learn in this course. You don't have to be a scientist or engineer trained specifically in this in order to discover this. You could be an amateur, such as these medical doctors, Poiseuille and, oh, by the way, Hagen, the German who published Poiseuille's formula a few months before Poiseuille, was also a medical doctor. Anyway, they're amateurs. You've heard of Helmholtz? Another medical doctor. He was a military one. Being an amateur is okay. It means that you're a ball player who came from the street. You know, you play what came to you, not what the coach told you to do. And who cares about the color of your uniform? Forget that. You know, it's about ideas. So, what is new in what I'm going to show you? Well, look, from the stem to the branches, what happens to the D is not much. It's a change of factor 1. Okay, it's amplified by the power 4, but it is number of order 1, even raised to power 4, okay? What matters, or what kills you, is the length of the duct. You see? So, how about looking at this tale that is now in the second lecture as a drawing consisting only of lines and the length of those lines. Get it? And the problem that shows you what's going to happen next is a problem 4.1 in the textbook. It's a very simple problem. You have an area, meaning a territory of fixed size. I call it A. And this A has, let's say, 2 dimensions, L and H. And you are here. With the Mongols chasing you, you know, threatening your life. And your gate to freedom is only here, in the middle of the opposing side. Clearly, it is in you to run straight to freedom. But what's best for you? In addition to the fact that the shortest path is the straight line. Even better for you is to have the shortest of the shortest paths, and this is how you contemplate the competition between areas A of various shapes. For example, if A is tall, then good luck to you. Your run to freedom will take a long time. If the same area is shallow, this time I'll make it even more gruesome, your run to freedom will take a long time. And so you're left with a very simple problem of minimizing this distance as you vary the shape. Yeah, what is this distance? Let's call it D. That distance is obviously the square root of 8 squared. And then, by the way, this F is supposed to be in the middle of the top side. L divided by 2 squared. And you want to minimize this distance, subject to A being fixed, which is HL constant. You know how you do that. You eliminate, let's say, L at the expense of H, and you obtain that the competition between Roman 1 and Roman 2, and you find that the minimum of D. You can do that graphically. You can also do it analytically by taking the derivative of D with respect to H and setting it equal to 0. And you discover that the answer is that H over L must be equal to 1 over 2, which is what I drew here. In other words, the shape of the lawn across which you have to run the fastest to freedom is the one that I drew, which is in fact 2 squares or a path with a 40-degree angle. It's good to know this. This is like not money in the bank. It's like the $1 bill in your wallet, which is the smallest denomination. With that, you can build bigger sums. And those bigger sums, as I'll show you next, are fancier drawings in which this idea is used to the hilt, meaning not ad infinitum, but with purpose, And in the textbook, the first step in this direction was with regard to. So this time we're talking about constructing flow architectures using this as the building block, meaning flow architectures, the defining feature of which is the minimal length path. Meaning you don't worry about diameters, it's about minimal length. So minimal length design. And here's one such, in fact, the very first that we've done after solving this problem. Let's say you have we have to figure out the flow architecture between a line and a point. This is the source. And the line is the sink. And the sink is in fact a string of exits. And the exits are equidistant. The flow could go in the opposite direction. The string of ports could be the sources. For example, rain falls from above. It enters this territory from this upper surface, and then at the very bottom is the big sink in which that the earthworm is living. You see, deep in the soil, and the distance between these ports is d. When it comes to wet soil, d is dictated by the length scale between pebbles or large grains that are covering the surface of the dirt. You know, the soil is not, what do you call this thing? Like chocolate fudge, you know, something without structure. it has a structure galore. In fact, it even has life inside the soil. Even things that are rotting are actually full of flows. So you get this equidistant configuration. And well, if that's the case, then why not recognize a multitude of these rectangles? And below, I mean, through these rectangles, the flow with minimal length goes easiest or fastest this way. See that? So if this was D, then this is D. Now what next? In other words, you go from this vertical dimension to a dimension that's twice as big. Then in the next step, you double the vertical dimension and construct a rectangle with an aspect ratio 2. And in this new rectangle, you allow the flow to continue this way. On this other side of the board, you have the same thing going, and then the same thing. Then you get the idea that so you double that and double that here. That the path to to the so-called sink or source completes itself this way. So this is how you discover fastest, the cheapest drawing that connects a line to one point, or vice versa, point to line. And you're not born yesterday. You know what you have neglected. You have neglected the fact that channels in reality should be thicker the closer you get to the, meaning when you get to the larger dimensions. So now you have 3 dimensions, big, medium, small. And you can calculate the flow resistance through this structure. But I'm postponing that step just a little bit because there is a punchline that has to do, well, naturally, with how good is this idea? I mean, how useful is the secret of making drawings? Well, imagine a layer of soil, and rain comes in from the top, then it seeps into the soil through the pores, and eventually it arrives at the water table. And there are at least two ways in which to to cross this thickness. One is seepage. Seepage, invisible, you cannot draw it, but basically is this sort of, the other name is diffusion, meaning viscous diffusion between the grains. It just flows as a plane front that marches slowly downward. So that's one way. The other way, presumably more intelligent, is to flow this way. I'll just draw, so I have to make a drawing with a 90-degree angle here. That means 45 degrees, so 45, and then 90, and then of course you do that. So that's the flow from top to bottom. But down here, you need to have the same sort of image that you see when you look from the top. And then you pair the first with itself turned upside down. So from the outside, you have equidistant entry points, and from below, equidistant exits. And that's respected here. See that? And the same here. And the question is, which flow is easier? And in the text you'll see, I hope I put it there, you'll see how to figure out the answer. You compare the flow resistance with the delta P across in this configuration. By the way, this calculation will depend on the number of bifurcation levels, which in this drawing is 2. You compare this drawing with an equivalent drawing in which the flow, the so-called the seepage, is a bundle of slender tubes with Poiseuille flow. Poiseuille flow is the cheapest model of seepage through a material with very small spacings between the grains. All right, and so this is delta P. Call it, I'll sketch it this way. This one is delta P with trees alternating with upside down trees. And you discover that the drawing on the right is better, actually better by a lot, when this n is greater than or equal to 4. Which in the soil, which is complicated, and earthworms and everything, earthworms are down here, is very easy to have. And this is why nature is really complicated if you don't have a shovel to stick into the wet ground and to discover the drawings of the invisible, you see. And because of this the cover of the book here at the bottom has a a montage of real trees alternating with upside down trees. Meaning there's only one photograph of a tree, which was repeated this way and this way to show you this sort of idea